Good morning or afternoon, whenever you are watching this. We are going to go over lesson 1.1. So we're switching to a new module today, which is all about understanding ratios. So we're going to jump into the presentation. I'm going to give you a few examples of how we're doing things, and then you can work on your homework. And as always, if you have questions as you're working through homework and stuff, please let me know. So the big question that we are going to be exploring today is how can you use reasoning to maintain the same relationship between two quantities as one of the quantities change? And basically what that means is we're setting up equivalent ratios. So we're given a situation. It says the students at Madison Middle School are going on a field trip. The principal requires one teacher chaperone for every 8 students attending the field trip. We're going to drag a possible combination of students and teachers onto the bus to then figure out if that ratio would work. So remember, the student-teacher ratio is 8 to 1, right? One teacher for every 8 students. So if I put one teacher on the bus, I would then need to add 8 students. Oops. There we go. 3, 4, 5, 6, 7, and 8. And if we're able to press go and the bus moves, then our ratio would be correct. So there we go. Our bus moves. So that means our ratio is correct. Now, if I were to only put one teacher and let's say 3 students, our bus would not go because that's not an equivalent ratio. Now, if we were to explore some other things, so what if the ratio changes some way, one of the quantities changes? What if instead of 8 students, we now have 16 students? How many teachers would we need to then put on the bus? Well, if I only put one teacher on it, right, the ratio would only be 1 to 16, right? So if we test that one, nope, doesn't work. So I'm going to try 2 teachers. I'm going to try that. That one would work because we've doubled the amount of students, right? We need to double the amount of teachers. So 8 times 2 is 16. 2 times 1 is 2. Then that works. One of the buses has 21 students and 3 teachers. All right, sorry about that. We had the morning announcements and I forgot that it was going to happen. So we had a little announcements here. Now, okay, so one of the buses has 21 students and 3 teachers. Now, if I were to do this, right, 21 students, right, and 3 teachers, the bus would not go because it's not an equivalent ratio. We'd have to then say, okay, well, if we had 1 to 8 as our original ratio, 1 times 3 is 3. 8 times 3 is 24. So we would actually need 24 students on this bus to then make the ratio equivalent. There we go. It works. Once again, we have another student to teacher. Okay. Situation, we have 32 students and 1 teacher. Well, 8 times 4 is 32, so we should have 4 teachers. So we need to add an additional 3 teachers to the bus. And then it would work. Okay. So the biggest thing to think about when we're talking with ratios is we need to do the same thing to both parts of the ratio. Okay. So when we're asked the question again, how can you use reasoning to maintain the same relationship between two quantities as one quantity changes? Whatever you do to one, you have to do to the other, okay? It's super important that if you adjust one side of the ratio, you do the exact same thing to the other. You want to think of ratios as like a scale. If we put too much stuff on one side of the scale, it'll tip, right? We need to have it balanced. So whatever I add to one side of the scale, I have to add to the other. Now in our next question here, we're given a table. So it says what we use to make 10 cups of lemonade. Now, what if we needed more lemonade or lemon juice, right? How does the number of cups of lemon juice compare to the total number of cups of lemonade? So in this situation, we're comparing a part to the whole, okay? So if we have 2 cups of lemon juice, we would then look at how much is their total amounts of liquid, right, that we would use. So remember, we're using 10 cups. So we would be comparing 2 cups of lemon juice to the total, which is 10 cups of lemonade. Okay? So when we're making a ratio, we can use that word for every and for each and that kind of thing. And it says here, we're going to select the buttons to see how the number of cups of lemon juice compare to the total number of cups. So if we have 2 cups of lemon juice, right, there we go. If we had 4 cups, right, we're just doubling everything, or 6 cups, we're still doubling, or we're then multiplying by more, okay? So see how the quantities change as we adjust those ratios. Remember, whatever I'm doing to one box, I'm doing to all the boxes to keep everything equal. All right, so Pedro mixed 2 sample containers of blue paint with the 3 sample containers of yellow to create his favorite shade of green paint. Pedro realized he did not have enough paint, so he added 2 more sample colors of each containers of each color. Will the new mixture be the same shade? And we're going to justify our response by then examining our results. So this is a part-to-part ratio. For every 2 containers of blue paint, there are 3 containers of yellow paint. Okay, so we need to make sure that it stays the same. So when we add, right? So here we go. 4 to 5, or 2 to 3, I'm sorry, is the first ratio, right? 4 to 5, is that the same? Well, we doubled the amount of blue paint, but did we double the amount of yellow paint as well? Now remember, 2 to 3. 2 times 2 is 4. 3 times 2, is that 5? No, that's 6. That would not be equal. So if we do not have an equal ratio, the ratio is not maintained, right? The color of green will not be the same. So we would need to add at least 1 more can of yellow paint to make sure that we have the correct shade of green. Now, are there other ways we could have made this mixture and still end up with the same shade of green? Yes, of course. So like we originally stated, 2 to 3 was the original ratio, right? We could double. That's 4 to 6, 8 to 12. We could have done, let's see, 6 to 9. All of these are equivalent ratios. They're all the same because what we're doing to one side of the ratio, we're also doing to the other. This is times 2, this is times 4, this is times 3. I'm going to skip that one. Sorry, there we go. So now we talked about part to whole and part to part ratios. Remember, when we're doing part to whole, it's when a ratio compares one part of the group to the whole group. So that's where we used our lemonade situation. This is the lemon juice. This would be the total amount of lemonade. Part to part is when we compare the amount of lemon juice to that what's not lemon juice, right? 7 cups of water, right, in this situation. So we would have the ratio of 2 to 7.